Hello everyone, after a lot of space news events today I'm finally getting around to talk about something slightly more theoretical again. I am still pushing back some updates on the SpaceX BFR prototyping situation, and I'm still editing and subtitling footage from the ELA airshow, and yes, Verse or Times Innovation still hasn't gotten around to doing 4 stupid clicks to clean up their mess of incompetence. While I'd still recommend to stay civilized by now, I'd say feel free to loudly complain and or flame. Either way, today I will get back to talking about physics, specifically something circulating on the internet, which is a field I should probably comment on more often. Generally the field of online science facts, some of them more accurate, some less. Online debates, some of them more stupid, some more interesting. And hypothetical questions and riddles, some more basic and some more complicated, because it turns out even the most simple and or annoying low-level physics debate can actually get quite interesting if you go further into detail, and you might even learn something even if you already understand high school level physics. So I thought I'd use these opportunities to comment on online debates as an opportunity to also talk a bit deeper about some physics-related topics and teaching the more interesting, deeper underlying understanding of physics. However, with all the negative connotations about online facts and debates out of the way, today I'm actually going to examine an image or fun fact that, while being a little bit oversimpled, is actually basically correct. It just tends to spark online debates where people who don't understand physics incorrectly argue that the image is supposedly completely wrong. So I will evaluate this image and go into the details, going off on lots of tangents, each of which hopefully will be somewhat interesting to you. Although this is a purely hypothetical scenario, the image in question posts that if you drilled a hole through the Earth, it would take you about 42 minutes and 12 seconds to fall through, and then you would come out on the other side and fall back in and through to the side where you started, and back and forth and back and forth. Now that time is slightly wrong, however that is very overly pedantic for a hypothetical scenario, so it is mostly correct and they have come to that conclusion with a very good reasoning. I'll eventually come around to explain why exactly it is slightly wrong, but first of all let's examine the rough scenario itself. So let's start with the possibility of this at all. What would you have to do to drill a hole through the Earth? Now the thing is, this is actually hypothetically possible, but incredibly expensive and difficult and outside of our technological reach. The deepest holes we have drilled so far go some 12 kilometers or so down, which is roughly the thickness of the Earth's crust. For obvious reasons, the deepest holes tend to be in locations where the crust is relatively thick, for the simple reason that if you're in a location where the crust is a little bit thinner, you can't drill that far down because you can't possibly drill beyond the crust. Now with today's technology there are a lot of challenges to drilling deep. There are problems with the drill length, how long can you make a drill or really any hanging object before it just rips apart under its own weight. Then there's the need for cooling and equipment, and basically you have to start with a very wide hole and get narrower and narrower as you go deeper, because you need space above for stops in between for equipment, for cooling, and you can only start with so big a hole. There's only so big a hole you can reasonably drill, and you can only get so narrow as well, so there's a limited range that you have to operate within. Temperature, pressure and technology somewhat limit us, and of course you can't drill any deeper than the crust. The Earth is hot and liquid inside, and you can't drill into a liquid, and you can't even reasonably drill anywhere close to it. But you could hypothetically build a giant, airtight, well-cooled and heat-resistant tube that you could push into the Earth's inside, which would be incredibly complicated and expensive, but it's hypothetically possible. Now, first of all, this has to be a vacuum chamber, because the thing with the Earth's atmosphere is that it gets exponentially thicker as you go down, or exponentially thinner as you go up. It's the same, just from a different perspective. However, that is not some weird quirk of our atmosphere's properties, that is basic physics at work. The air pressure on the ground is really just the weight of all the air above you pushing down on you over a certain area and thus creating a pressure, and that pressure again increases the density of the air around you, and the more dense the air around you is, the faster the weight of the air above you increases as you go down, as there's more air that goes above you, and the faster the pressure increases. And while there are a few deviations, because under extremely low pressure, temperatures in its definition starts to fall apart, and because air is not a very ideal gas, and its composition changes, and so on and so on, roughly speaking, what we have here is a function that is its own derivative. The rate of pressure change is proportional to the pressure, and thus we get an exponential equation. One that does not simply stop at the ground. The thing is, if you drill a very deep hole, and that hole in its diameter is not relevant to the Earth's overall size, so the surface pressure of the Earth's atmosphere doesn't change, so if you drill a very deep hole, the pressure keeps rising as you go down that hole. And after going some 50 or 60 kilometers down, the air would actually become almost liquid, or at least so dense that it would be more similar to what we know as water than it would be to air, at least in terms of physical properties. You could basically swim in it. And if you were falling down, you would basically impact it hard. So in order for this entire scenario to work out at all, it would also have to be a giant vacuum tube sealed from the ends. It would have to be well cooled so you don't get grilled on the inside, and you would have to wear a spacesuit to jump through, but it's still a viable hypothetical scenario. Now once that hypothetical scenario is at least as a hypothetical scenario accepted, there are mostly 3 different opinions on it. Which of course doesn't really matter because science and physics don't really care about your opinion, but they're still kind of interesting, especially in the ways that they come to these conclusions, as that can teach us something about scientific models. Now the first opinion is that of people who either assume that there is air in the tube, which would slow you down and dampen you, and basically instead of falling down at orbital speed would make you slowly drift and sink to the core, which of course is reasonable, but then you'd also have to assume that you would be crushed under an exponentially increased pressure. Now this in and of itself makes sense, but the same result or the same opinion is also shared by people who do assume that there's no friction but don't understand basic Newtonian physics and assume that if you're down you just stay down, you're locked at the core because that's where gravity pulls you, which of course is also bullshit because you still have a lot of inertia going. And of course the conservation of energy requires that unless there is a lot of friction, you would come out at the same altitude or the same depth at which you jumped in, plus minus a few meters for terrain difference or the speed at which you jumped in or irregularities in the Earth's gravitational field. But if you were accelerated downwards by a gravitational field, then you have enough kinetic energy to go the same distance upwards in the same gravitational field. You can compare it to a bouncing ball under the assumption that it would be perfectly elastic, or an orbit with a fixed apogee, or an object coming by at escape velocity. Now the truly interesting debate is which side you would come out on. And I can spoil it up ahead, you would come out at the opposite side. However, there is a good or a understandable reason why people would think that you come out on the same side, which comes down to orbital mechanics and approximations and simplifications that we use. The thing is, in orbital mechanics or in most of physics, we often assume that all of the Earth's mass is concentrated completely at its core. A simplification that works almost perfectly well as long as you stay outside of the Earth, which is where most satellites and aircraft and people and physics problems take place. However, it falls apart as soon as you dig down into the Earth, and in fact, well, the mass of the Earth is distributed throughout the Earth. If you assume that it's all concentrated at the core, then we would have a black hole at the core, but let's ignore that. Then also, if you approach the core, your gravitational field would of course get stronger because you're getting closer to the source of gravity. And in fact, if we are looking at basic orbital mechanics, and well, if we look at, you have an apogeum, which is where you jump in, and we know that the orbital velocity for a circular orbit at this altitude would be very, very high, and you're at a much lower velocity. So basically, we can follow up with Kepler's orbital mechanics, that your perigee would be very, very low, and you basically swing around the Earth's core, where, hypothetically speaking, all the Earth's mass would be concentrated in a black hole, and you would actually swing back up to the same side that you jumped in on, and back to the same altitude on that side. Since orbits are elliptic and repetitive, at least in a two-body problem, you always come back to the same point in your orbit at the same place. Your apogee and perigee are not suddenly going to switch sides. And we can easily calculate how long that down and back up fall would take using Kepler's equations, since we basically have an orbit with half the semi-major axis of a circular orbit, and the orbital period is proportional to the square root of the semi-major axis to the power of 3, we come out at about half an hour, which is relatively short, but it makes sense that it would be shorter than the actual time, because we're assuming that all the mass is concentrated at the Earth's core, which means that you're subjected to a lot more gravity and thus get a higher velocity while you approach that core. Now the thing is, this is a very common misconception, because this is what many orbital mechanics calculations tools do. This is what the orbital predictions in Kerbal Space Programs or the Orbit MFD in Orbital Spaceflight Simulator would display you, since these are made for spacecraft that fly outside of the Earth, and thus, well, they reasonably use an approximation that only works for this circumstance. Now if we want to calculate the actual time that it would take, we have to go to the reasoning behind that approximation in the first place, and that would be the shell theorem. The shell theorem is a mathematical theorem that was proven by Isaac Newton, who was of course at the time working on gravity and already had this application in mind, but actually it's just a mathematical or geometrical theorem that also works on anything that has a similar mathematical description to Newton's gravity. Basically, it works on anything that declines with the inverse square law as distance increases, which of course is very interesting if you have seen my video on four-dimensional orbital mechanics, but for now we'll just accept that gravity works in the inverse square law. If you go twice as far away from something, the gravitational pull between you and that object gets weaker by a factor of 4, and using that assumption and Pythagoras and trigonometry, Newton set out to mathematically prove the shell theorem, which applies to hollow spheres, and the proof shows that if you are outside of a hollow sphere that has an equally distributed mass over its surface, then the gravitational pull between you and that hollow sphere is exactly the same as if all its mass was concentrated at its center. Now we can see where the approximation of all the Earth's mass at its center comes from. Now the Earth is of course not hollow, even though some conspiracy theorists with a complete lack of basic educations may claim so. But of course a solid sphere is basically nothing else than a lot of hollow spheres of different size nested within each other, all of them sharing the same center and thus simply adding up according to the shell theorem. So you can see why the approximation of assuming that the Earth's mass is concentrated at its core works as long as you stay outside of the Earth, and it even works with the Earth's mass being unevenly distributed over depth as long as it is evenly distributed along its surface, which isn't exactly true, but it's close enough that this approximation is used in orbiter and basic orbital mechanics, and even if more precision is needed, this is usually used as a basis and further disturbances are just added up to this. However, the shell theorem has a part 2, and remember that in part 1 it said that as long as you are outside of an hollow sphere, its gravity on you will be as though its mass was concentrated at its center. Well, part 2 says that if you are inside of a hollow sphere, its net gravitational pull on you will be exactly zero, which also somewhat makes sense, because if you are at the center, then of course there is the same gravitational pull in each direction, just evening out, and if you deviate slightly from the center, then well, there is more of the sphere to you in one direction, but you are closer to the parts in the opposite direction, and this actually evens out, and it was mathematically proven that the net gravity is actually always exactly zero. That is, for a hollow sphere, and if again we imagine the Earth as a infinite number of hollow spheres nested within each other, as you start digging down, you start to go inside some of these hollow spheres, and as by the shell theorem, these become irrelevant to you. And the mass that you can approximate to be at the center of the Earth is now only the mass of that part of the Earth that you're still outside of. It's basically like being on a smaller and smaller planet, and while you do get closer on it, which means its gravitational pull gets stronger in a square function, it also gets smaller, and with any volume or mass by constant density, that is a cube function. So in the end, if you cancel that out, you get the result that if you start digging into the Earth, your weight or gravitational pull will decrease, and it will basically be proportional to your distance from the center. At the center, the gravitational pull is zero, and the further you go away from it, the stronger your gravitational pull gets proportionally until you reach the surface. And only when you reach the surface, the other approximation for outside of the Earth can be used, where your gravitational pull gets weaker in a square function, and you get working Kepler orbits. Now the interesting part for this scenario, where, well, within this hypothetical scenario, you're inside the Earth all the time, so for this scenario we can say that the gravitational pull is actually proportional to your distance from the Earth's core, which is very practical because it means that this is basically a sine function. Your gravitational acceleration is the derivative or rate of change of your velocity, and your velocity is the derivative or rate of change of your position, and your position or distance from the core, as we've just seen, is proportional to your acceleration, and the acceleration is towards the core, so we can see that this is simply a function that is negatively proportional to its own second derivative, or a sine function. Now we could go through the period of sine functions and the Earth's mass and the gravitational constant and calculate the period of that fall through. The interesting thing is that it's actually the same as the orbital period of a satellite orbiting the Earth, if it was orbiting at surface altitude, which of course isn't possible, but you can still calculate a Kepler orbit, a hypothetical Kepler orbit, with an altitude of 0 that goes on the Earth's surface. And since, for example, low Earth orbit spacecraft aren't that high above the Earth's surface relative to the Earth's radius, it's pretty similar in result. We can show why this is the case, because we get the same sine function for each coordinate of an orbit. If we imagine a circular orbit, then the overall amount of gravity is constant, since the distance from its planet is constant, and with that the component of the gravitational force in one direction or one coordinate axis is proportional to the satellite's position along this axis, since the gravity always points towards the center. So yes, the time you would take to fall through is half the time that a satellite would need to orbit the Earth, since, well, it only goes halfway round, and by the time you fall through again and you're back on the side you initially jumped in on, the satellite is also back where it was when it started. And this actually gives the result that the fun fact picture on the internet gave us, and now we're getting really nitpicky. Because the thing is, Earth's mass is not evenly distributed through its volume. The heavier elements tend to be closer to the bottom or closer to its core, while the lighter elements tend to be on top. Now this isn't a linear distribution, it gets very, very complicated, but you can get some rough approximations for the distribution of density through the Earth's depth, and this isn't going to have a very large impact. The mass is still far from being completely concentrated at the core, And you're not going to do a rapid black hole swing by at the core and flip back up to your original side, but as you can probably imagine, this does slightly speed up your travel through the Earth's core. Since the lighter elements are on top, as you go down, the hollow spheres that become irrelevant to you are lighter than average, while the core that always stays relevant to you is heavier than average, so mid-flight the gravitational pull on you is stronger than average, meaning you build up a slightly higher velocity, and I've actually done a rough numerical approximation of this, and it comes out at about 39 minutes for a whole jump through the Earth, so actually a relatively small difference, just some 10%, even though the core is way above average density, since, well, the gravitational pull at Earth's surface was assessed correctly, and this only starts getting different the further down you get, and that is only relevant for a very short amount of time, so the big difference between the simpler model that was used in that image and the more detailed model with a very rough approximation of Earth's density distribution over depth are only really different as you go far down, and that is only a relatively short distance to cross. Of course, another fun thing to keep in mind if you're nitpicky is that you would either have to drill your hole from one pole to another, or you would have to curve your hole to take Coriolis effects into account. As we all know, the Earth rotates every 23 hours and 56 minutes, or roughly 24 hours, and as the Earth rotates and its surface moves, you move along with it. But if you get closer to the Earth's axis, you actually move slower. Now there's this old comparison that I'm afraid is a bit outdated now, but there used to be records, basically round plates that would spin around to play music. Not getting into detail on this now, but the older generation might still know it, while younger generations might only know MP3 files. This was often used as an example to explain that, well, if you're closer to the center around which it spins, you only move a relatively small circumference with every rotation, while if you're at the rim of that record, you will move a very large circumference with every rotation. But inertia, following Newton's laws, doesn't really care about this. You move on at the same speed that you used to when you were standing at the surface. So to fall through the Earth in a straight line, you would have to slow down and get to zero as you pass the Earth's core, since obviously the Earth's core doesn't really shift with Earth's rotation, it is the center around which it rotates. And of course the opposite side of the Earth moves linearly in the opposite direction as the Earth rotates, so you would have to speed up again in the opposite direction. This doesn't happen, so your tunnel would curve weirdly, and as you reach the other side, you would have twice your tangential velocity in velocity difference compared to the surface or any building on it, so your tunnel would have to weirdly loop around, and actually it wouldn't get back to the exact same place that you started anyways. I've included a rough plot of what that would look like in my simulation, although this is the absolute trajectory that you actually move along, since the Earth would spin away underneath it. The tunnel would have to be reverse curved against it again. It would get a weird, almost 8-like shape. So if you actually want to do this and you don't want to risk wasting trillions upon trillions upon trillions on dollars on this project for nothing, I would recommend drilling from one pole to the other rather than from one point on the equator to another. Now, while we're on this hypothetical concept, it does actually have an application. It's incredibly impractical and overly expensive, but if we had such a tunnel, say for free, it could actually be useful for launching rockets to escape velocity due to the O-berth effect, which is that fuel burned at a lower point in a gravitational field is more efficiently used. That basically comes down to energy being impulse times velocity, or power being force times speed. A rocket engine given a constant thrust can more efficiently add energy to your trajectory if you are already going fast. So the absolutely ridiculous difficulty and expense of building such a hole aside, if we already had such a hole for free with a vacuum tube and all, the most efficient way to get to escape velocity or an interplanetary trajectory or to the moon would actually be to dump your rocket into that hole, burn all your fuel as you pass the Earth's core already at orbital velocity, and then let it come up again with some energy left, with some velocity left, more velocity than the delta V you burned at the core, since, well, kinetic energy is squared. You can simply use the orbital velocity, which is roughly the velocity that you would have at the core, and the conservation of energy and the formula for kinetic energy to calculate how much delta V you can save with this. And well, if you were going to escape velocity, you would save about 50% of your delta V. Now extend the sealed vacuum tube to reach outside of the Earth's atmosphere on the other side, which in itself is already an incredibly expensive and difficult project. But then you could hypothetically save a lot of fuel, but it's not really worth it at all. Though it is good to mention, since this is a hypothetical scenario anyway, and this would be an interesting thing to consider within that scenario. I hope you found this a little nitpicky, too far in-depth going on online science discussions somewhat interesting, and might have learned something on one of the long tangents I went on. If you have any suggestions or any questions about spaceflight or the physics behind it, I'm always open for requests, and as always, thanks for watching.